So hello everybody. So now let us continue our discussion further with respect to the channel-like structures or clatrates, where now we will be considering pure organic molecules as a host which will form a supramolecular structure and create voids into which the guest molecules can sit. So to start with, let us consider organic molecules forming clatrates, and then they can include different guest molecules, for example water. So we can take the example of trimesic acid, and trimesic acid has been observed to form different kind of complexes with water. And what is also very important is the kind of supramolecular host like structure the trimesic acid forms to include different kind of guest molecules. So we have different building blocks when it comes to the trimesic acid. Let us look at the building blocks. CO2H, CO2H, CO2H. So we have got these carboxylic acid groups. Now it can form hydrogen bonds, the OHO hydrogen bonds. Okay. And this can further interact with you have the acid here. One, two, three, four. One, two, three, four, 5, and now we can have the last one, which will be OH, and so effectively these will be hydrogen bonded as well. So now this forms a 1, 2, 3, 4, 5, 6, a hexamer. Cyclic hexamer motif like structure, and now you can see that there is a large void in the center. So this can actually have the guest molecules. For example, we can have water molecules which are present, and the water molecules can also associate by hydrogen bonding, and thus trimesic acid forms these channel like structures. You have a channel and into this channel you will have the voids where you can have the guest molecules. So this creates a hexagonal channel like structure. and the dimensions of this cavity are pretty large, that they are able to also include organic molecules as well. There have been reports where different kind of organic molecules which are actually liquid at room temperature have been crystallized along with this trimesic acid. In other words, trimesic acid has been found to be a very good crystallizing agent. For example, if you have a molecule, a drug molecule, say for example, a drug molecule which is liquid at room temperature, and you would like to determine the structure of the compound, but it is a liquid at room temperature. So, what we can actually do is that we can actually template and crystallize this drug molecule along with this trimesic acid, because the trimesic acid forms a structure which has got large voids, and into the voids the drug molecule can go and sit, and from X-ray crystallography you can now determine the three-dimensional structure of the drug. So, this is an extremely useful approach, that is utilizing the concept of channel structures, a supramolecular host, to include different kind of molecules of different shapes and sizes, crystallize them together with the trimesic host and determine the structure of different kind of molecules which are liquids at room temperature. You can also take metal complexes, you can take organometallic complexes, and you can try to crystallize them in the host framework of this trimesic acid. And you can also do chiral drugs, because chirality is very important, and we would like to know which particular enantiomer of the drug has crystallized. So, the pure drug, which is the enantiomeric form, can also be crystallized and the structure can be determined. So, trimesic acid has got very unique applications in functioning as a supramolecular host to include solvent molecules as well as drug molecules. Now, we can now go to the next example, which we refer to as. So, we can now go to another case where it is not necessary that you have an intrinsic void associated with the crystal structure. There are many cases now which has been observed that even if there is little bit of space available and you have got a particular guest which can actually kind of occupy the little bit of void space which is present, then also it is able to form a host guest complex. For example, this motivation of trying to include guest molecules into a crystal structure which does not have any voids to start with. So, the question is that can we include guest molecules into crystal structures where the voids available is very less, and what kind of gas can we select to include which can be included into these voids. So, the motivation came from this work where people have crystallized benzene and hexafluorobenzene, and on the basis of the fact that both being low temperature solids, melting point of benzene is 5.5, hexafluorobenzene is 5.2. So, they are both liquids at room temperature, but when you actually make a co-crystal or you make a 1:1 donor acceptor complex, then the resulting compound, the resulting co-crystal melts at a much higher point. It is a solid below 24 degrees centigrade. And you can see very clearly from the molecular electrostatic surface potential that there is a nice complementarity which exists. The C6F6 has got positive electrostatic potential, and benzene, the central region, has got negative electrostatic potential, and it is the complementarity between the negative and the positive electrostatic potential that favors the stacking of these host guest interactions, or you can say the donor acceptor complexes. So, with this in mind, it has been demonstrated that if you take this particular substrate and ethanol substituted benzamide, and it has also got an amide functionality in the center. So, there is a strong donor and there is a strong acceptor, and you take different substituents and different isomers. So, you can have R equal to fluorine, the ortho meta para isomer. You can have trifluoromethyl group, ortho meta para. You can have the chloro and the bromo and the 3 different isomers. So, you can have a set of 12 molecules, and then you can try to understand the inclusion behavior of this hexafluorobenzene, because benzene is relatively electron rich, hexafluorobenzene is electron deficient, and can they interact with each other. And after a careful investigation of the crystal structure, these are the views of the donor acceptor complex. You will see that the hexafluorobenzene sits above the phenyl ring via the stacking interactions. The same thing happens when you have the fluorobenzene moiety interacting with hexafluorobenzene. Now, when you change it to the other isomer, the meta isomer, the para CF3 isomer, which obviously is a different molecule. So, also in the case of TF, when you have a trifluoromethyl, again the hexafluorobenzene interacts with the same benzene ring having a CF3 substituent, same for the chloro. But now, when you go to the metachloro, surprisingly it switches over to the ethanol substituted benzene ring, and there we see and we have the interaction between the donor and the acceptor, and when it is bromo, again it is on the ethanol side. So, you get this interesting set of inclusion complexes with hexafluorobenzene as the guest included in the crystal structure of the host molecule, which is the ethanol substituted benzamide, and what favors here these stacking are the pi-pi interactions. And it is also very clear from the electrostatic potential that why these donor acceptor complexes are very tightly bound. For example, we can see this is the electrostatic potential surface of the benzamide molecule. You can see the negative regions in red and the positive regions, which are the hydrogen atoms, in blue. And the hexafluorobenzene, this is the MESP of hexafluorobenzene. You can see that the fluorines are highly electronegative, so the electrostatic potential is negative. For the central part, it is positive. So, it is now the complementarity between this positive part and the negative part of the benzene nucleus or the ethanol substituted part, which actually allows for these donor acceptor interactions to take place, and this is well exemplified in all the cases, which very well demonstrate the nice electrostatic complementarity between the negative region of the ethanol substituted benzene ring as well as the positive region of the hexafluorobenzene. And this is what actually drives electrostatic interactions, is what drives these kind of pi-pi stacking, and nicely demonstrated in all these complexes. Along the same lines, we were also interested to see that whether there can be some structural changes. As we already looked in the previous lecture, we have a parent molecule which need not have the solvent, that is called the apohost, and it can also include the solvent, that is called the solvated form, and we can actually modify the structure of the solvated form to access different phases. Now, here in this particular compound, a specific molecule, a para-fluoroethanol substituted benzamide, what was observed is that you can see now the crystal structure. In the crystal structure, you will see that as such there are not much voids, but what is the available volume? You see, this is the available volume in the parent structure. So, if you now look at the available void or the space, now you can see the hexafluorobenzene is a planar molecule. It's like a flat molecule, and it is able to easily intercalate and get included into this void which is present down the plane of the board or down the plane of this computer. So, now you can see very nicely it goes and sits in the voids. It is stabilized by the pi-pi stacking, but overall the stabilization is not very much strong, and desolvation can easily take place. When desolvation happens, you will see that the solvent goes out and there is some change in the volume, but overall the packing remains compact, and you see this is the void space which is available for the hexafluorobenzene to go and sit. At the same time, you can see that there is no solvent or hexafluorobenzene sitting between these pi rings, and there is some change in the the distance between these pi rings as well. So, this opens up a bit, and you can see here that the primary crystal packing is the NHO hydrogen bonds, which is actually held by these weak CHF hydrogen bonds. So, both strong hydrogen bonds as well as the weak hydrogen bonds who create this three-dimensional structure, and the voids which are available as shown in pink can now include the hexafluorobenzene. This is to show the shape requirement, the volume requirement, that it is very nicely fitting. The volume requirement of hexafluorobenzene is such that it is very nicely fitting into the voids, and which is created. But then these voids the structure does not have intrinsically high porosity or high void volume. They are just able to intercalate, but they can also be easily removed, and this desolvation process now results in a single crystal to single crystal phase transition, where you can see that the final structure does not have the solvents. The solvents have essentially been removed, and there is a partial collapse of the structure, in the sense that now the molecules come close to each other, thereby indicating that desolvation can happen in a very facile way in the structures without the loss of crystallinity, and thus we are able to determine the structure after the loss of the solvent. Normally, if the solvent is expelled or the guest is expelled, the crystallinity is lost and the structure collapses, but in this case we are very nicely able to capture the single crystal to single crystal phase transition. Now, with this in mind, let us go to another example to complete the discussion. We will now look at Dianin compound, which is also called a hexa-host strategy. Dianin compound, which is also called a hexa-host strategy. Now, let us look at the structure of a Dianin compound first. The motivation came from the fact that we have phenols which can form crystal structures containing OHO hydrogen bonds, and we can now make this is oxygen, this is methyl, this is methyl, and we have got the substituted phenol. So, at the para position we have replaced it by this particular hydrophobic moiety which has the oxygen atom here, and this is a chiral center. So, this is a chiral compound which is called the Dianin compound, and this compound has is very versatile, is very unique, because it has been found to include large type of guest molecules in the crystal structure. So, what is unique about the Dianin compound? So, the Dianin compound forms a hexameric host structure. And how does it do? So, we have the R OH So, here we see that this is the hexa host. You can see the OHO hydrogen bonding, and the R groups are anti to each other. Okay, so if the first, so this R is top, the next one is bottom, then it is top, then it is bottom, it is top, and then this is bottom. So, we have this top, up and down arrangement of the R groups such that it minimizes the sterics, because this is the R group here. Okay, and the formation of the hexa host is driven by this OH group, and you have this one particular hexa host, and then there is another hexa host arrangement in the bottom, and in between you will have here also some R groups will be present. Okay, so you have got 1, 2, 3, and then you have got so you have got this. So, you have 3 R groups in the top, 3 in the bottom, and now you see that there is a void which is created here, and this void can now include different guests. So there is one hexa host in the top, another hexa host in the bottom, and there is a lot of void space now available into which the guest molecules can go and sit. So this is a very unique structure type, and this shows very clearly the cage like structure which is present in the hexa host dianin compound. And the next question was that can we maintain this host structure by modifying the substituents or by modifying the atoms which are present either on the ring or on the phenyl side. So whether modification will allow us to maintain this inclusion behavior. So now we see it is, now we can say that dianin's compound, I am writing it as DC, it is a versatile host because of the formation of this hexa host complex and two such hexa hosts forming a net structure that has voids that can include different kind of guest molecules. So it is a versatile host and it can include wide range of organic and inorganic guests. For example, argon, glycerol, sugars, and more importantly SF6. And what is SF6? It is an insulating gas used in electrical industry. So these are some of the interesting features of this versatile host, and what has been observed is that the ratio of host to guest is 6:1. So 6 molecules of the host and 1 molecule of the guest is present, and this is consistent with the hexameric structure. So the next thing is that what about the other compounds? So with ethanol, butanol and acetone, it forms 6:2 or we can say 3:1. That means 2 molecules of acetone or butanol or ethanol are present. In case of methanol, it is 6:3 because methanol is smaller in size compared to ethanol or acetone. So we have 3:1. In case of piperidine, it is 1:1. And what has been observed is that the solvent molecules like ethanol or butanol, they actually undergo a liquid like motion even at very low temperature inside the void structure. So the next question is that can we maintain the robust host structure by modification in Dianin's compound? Whether if we modify the Dianin's compound, can we actually modify the host structure, which is very robust? Why it is robust? Because of strong OHO hydrogen bonding and the formation of this hexa host. The clathret property or the inclusion property of this Dianin's compound is very much robust. So what we can now do here is that we can so what we can now do, let us draw the structure. So this is my Dianin's compound, this is my, I am labeling it as 2 and this I am labeling it as 4 number wise. So 1, 2, 3 and 4, and we can now do different modifications under different strategy. So, strategy 1 is perturbation of the substitution pattern at C2 and C4. This is strategy 1. Strategy 2 is changing the OH group to other functionalities like SH or NH2. Strategy 3, replacement of etheric oxygen, that is this one, to sulfur or selenium. And strategy 4 is addition of substituents to the aromatic ring. So, whether if we add some R1 or R2 group here, whether this particular hexa host remains constant. And what has been proposed is that it essentially has a structure of this type, where the dimensions are 280 picometer, 630 picometer, 420 picometer, and this is around 11 angstrom. So, overall this is what is the arrangement, and what happens to these dimensions or changes in the structure when you incorporate these strategies. So, according to the first strategy, the results are as follows. If you change the substitution pattern, so instead of say methyl, you put ethyl or propyl or butyl, or so now according to the results of the strategy 1, so removal of one of the methyl groups results in a host with a much wider cavity, results in a host with a much wider cavity. So, it becomes 7.1 angstrom versus 4.2 angstrom. So, this particular region here where we have the methyl groups, this becomes much more wider because the sterics are reduced. And then replacement of the C4 methyl group. So, according to the strategy 2, if you now replace this particular methyl group here, it forms a different structure that does not exhibit clatrate behavior. So, first we did a modification here, now we actually did the replacement of this methyl group and it does not form a similar structure. Sorry, this was still strategy 1, I would like to say. Now, strategy 2, if you replace OH with NH2, then again the clatrate property is lost. The clatrate property is lost. So, when if you this OH is very much important to form the hexa host. If you replace it with NH2, again there is loss in clatrate property. And when you strategy 3, if you replace oxygen with sulfur, then it still forms the clatrate property, it still has the clatrate property, and it has 6:1 stoichiometry, and it has a slightly wider cavity because now we have SHS hydrogen bonds. So, the cavity is slightly widened because of the presence of this relatively longer SHS hydrogen bond, and now the sulfur analog is very efficient in trapping dimethyl mercury, because this is a very toxic compound. So, this particular host, which is the sulfur analog of it, can be utilized to efficiently trap dimethyl mercury, and the resulting complex can be stored under high vacuum for several days. Only under high vacuum this is being stabilized. And if you now replace, and now according to the last strategy, if you now put different kind of substituents, for example, if you put R1 is equal to methyl, then it still forms the clatrate type of structure. However, the sizes of the cavities are going to change when you have done a replacement of R1 with methyl, and when you actually now fuse. So, when you now fuse another phenyl ring here, then now the structure completely changes and it does not exhibit any clatrate behavior, no clatrate behavior. So, you can now see the entire spectrum of changes, that you have first done substitution at C2 at C4, perturbation of the substitution pattern. If you do it for the, if you replace one of the, remove one of the methyl groups, it leads to the same structure but with a wider cavity, and but if you replace or remove C4, then it does not have the clatrate structure. Removal of OH, clatrate behavior is lost. Replacement of oxygen with sulfur, you have the clatrate structure, but you have a slightly elongated or wider cavity because of the SHS hydrogen bonds. If you, and that is a very good host for trapping dimethyl mercury, which is kept under vacuum, can be stored under vacuum, high vacuum for many days. And then modification at the phenyl side with methyl still maintains the Dianin's structure, however the cavities are modified, and replacement with phenyl again alters the structure completely, and there is no clatrate property. So, with this we have now seen the versatility of Dianin's compound and the spectrum of structures and host guest interactions it can have depending upon the structure of the parent compound. So, the parent compound structure is important, whether it creates the necessary cavity to now, and this is a organic, made up of organic molecule which can now include different kind of guests starting from different solvents to different inorganic compounds like SF6 or dimethyl mercury as well. So, with this we come to a closure of the discussion on host guest complexation involving clatrates. In the next lecture we will now go towards a new topic which is called crystal engineering. Thank you.